Today, we are going to briefly explore one of the most interesting and fascinating phenomena in numerology and all of mathematics, Pascal's triangle. So what is it?
Actually a mathematical treasure trove. Indian mathematicians called it the staircase of Mount Meru. In Iran, it's the Khayyam triangle, and in China, it's Yang Wei's triangle. To much of the Western world, it's known as Pascal's triangle, after French mathematician Blaise Pascal, which seems a bit unfair since he was clearly late to the party, but he still had a lot to contribute. So what is it about this that has so intrigued mathematicians the world over? In short, it's full of patterns and secrets. First and foremost, there's the pattern that generates it. Start with 1 and imagine invisible zeros on either side of it. Add them together in pairs and you'll generate the next row. Now do that again and again. Keep going and you'll wind up with something like this. Though really Pascal's triangle goes on infinitely. Now,
although the French mathematician Blaise Pascal is named after this cornerstone of probability and algebra, he certainly did not discover it. The ancient Indians, Persians, and Chinese all worked with the triangle long before, dating back as far as the 2nd century BC. So one of the interesting applications of Pascal's triangle is one that we've learned already in Algebra 2, which is all about binomial expansion. So if you recall, each row of the triangle corresponds to the coefficients of the terms when you expand a binomial in the form x plus y to the n power, where n is any of the rows in your triangle. So for example, if we wanted to expand x plus y squared, it would equal 1x squared plus 2xy plus 1y squared. And what I want us to focus on is the coefficient of each of those terms. 1, 2, 1 corresponds to the numbers in the second row of Pascal's triangle. And the same can be said for x plus y cubed, which would have coefficients of 1, 3, 3, and 1, which would correspond to the third row in Pascal's triangle, and so on and so forth. The next application we're going to look at is from combinatorics or probability. So for example, in Pascal's triangle, the row number will tell you how many objects you would like to choose from, and then the specific place value or number in that row tells you how many combinations you can get depending on how many objects you chose in total. So for example, let's say you have 5 different pieces of fruit in a fruit bowl, and you want to know how many combinations you can make by choosing only 2 fruits. 5 pieces of fruit, we're going to go to row 5. If I want to choose 2 of those, I'm going to go to the second place in that row. Now keep in mind the 1 represents the 0 place, so the second place in row 5 would represent 10. So there are 10 total combinations of fruit that you can choose from. Another application, as you can see here, is the sum of all the digits in any row is equal to 2 raised to the power of that row. The next application of Pascal's triangle is super interesting because we look at the Fibonacci sequence, which is one of the most famous mathematical sequences, which is created by adding together the 2 previous terms to get the next one. So your Fibonacci numbers would start out as 1, then another 1, then you add those to get 2, then you add those to get 3. And what you'll start to notice here is that as you take the shallow diagonals in Pascal's triangle, you are creating the Fibonacci numbers when you sum together all of the values in each of those diagonals. So yet again, another pattern that is created inside of Pascal's triangle. The last application we're going to look at are what's called hockey stick numbers. So as you can see, if you start with any number in the triangle and you proceed down in a diagonal, then change the direction of that diagonal for one last number, the sum of all of the numbers in the first diagonal are equal to the last value. And that, my friends, is a brief introduction and look into the mystery, intrigue, and awe of Pascal's triangle.